Welcome back to the ACE Summaries series. This video is the final installment in this series and completes the rest of the book. As always, make sure to download the PDFs from the server, for which I'll have a link in the description. And don't forget, please thumbs up this video so that I can reach more people. Chapter 8, Meteorology. An isobar on a weather chart is a line that joins areas of equal sea level pressure. Heat is measured in calories. It is described as the amount of energy required to raise 1 gram of water by 1 degree Celsius. Heat held in the Earth's surface can be transferred to the atmosphere through a process known as radiation, or conduction or convection. These processes significantly contribute to the weather patterns we see within our atmosphere. By day, cloud cover stops incoming insolation from reaching the surface by reflecting it into space. At night, the cloud cover instead stops heat which is accumulated on the surface from being transferred out into space. Latent heat is the energy in calories absorbed or released when water changes from one state to another. When water changes to a higher energy state, i.e. ice melting, it absorbs latent heat energy from the surrounding atmosphere. This is why when you put your hand above a boiling pot of water and the steam converts back to water, it burns your hand, because latent heat is released. When water transforms to a lower energy state, therefore, from a high energy state, it will release heat. Total air temperature, TAT, is the sum of the static air temperature and the ram rise caused by friction of fast-moving air particles against the surface or the sensory probe of an aircraft. Altimeters are calibrated using ISA pressure gradients. Therefore, when it's colder than ISA, this is the reason the true altitude will be smaller than what the altimeter is actually indicating. The correction is 4 feet per each degree of deviation from ISA per 1,000 feet. For example, when making an approach to an aerodrome at mean sea level in Siberia in January, the decision height is 200 feet. What is the true height when the indicated height is 200 feet if the temperature is minus 50 degrees Celsius? For this, we do 4 times minus 25 times 0.2, and we get minus 52. So 200 feet minus 52 is 148 feet of true height when 200 feet is being indicated. This means that you'll be 52 feet below minimums when your altimeter indicates minimums, because your altimeter is calibrated to ISA. Remember, if temperature or pressure below, true altitude is low. This means that if the temperature or pressure is below the ISA values, then your true altitude will be lower than your indicated altitude. Pressure error is 27 feet per degree of ISA deviation. Using this knowledge, we can solve the following. Note, remember to always add all altimeter errors together after calculating them before subtracting or adding error to indication. The question is, if an aircraft is maintaining flight level 180 in an area where QNH is 983 millibars and the temperature is ISA minus 25, what is the true altitude? First, we calculate the pressure error. 1013.2 minus 983 equals 30.2 millibars. 30.2 times 27 means we are 815 feet below indicated altitude. Now the temperature error, 4 times minus 25 times 18, gives us an answer that we are 1,800 feet below indicated. So the total error will be the sum of both these errors. 815 feet plus 1,800 feet means we are 2,615 feet below flight level 180. True altitude, therefore, is 15,385 when we are at flight level 180 in these conditions of 983 millibars and ISA minus 25. Lapse rate is a term that describes the rate of temperature change as your altitude within an atmosphere increases. The environmental lapse rate in the standard ISA atmosphere is a lapse rate of -2 degrees for every 1,000 feet altitude that you gain. The dry adiabatic lapse rate for unsaturated air is -3 degrees Celsius per 1,000 feet. After air reaches its dew point, condensation releases latent heat. This causes the saturated adiabatic lapse rate of -1.5 degrees Celsius per 1,000 feet to prevail. Provided there is a lifting action present, cloud base will be determined by the difference between the actual temperature and the dew point. In general, moister air results in lower cloud bases. The cloud base in feet can be calculated by temperature minus dew point divided by lapse rate multiplied by 1,000. Curiform are fibrous clouds. Cumuliform are heaped clouds. Stratiform are layered clouds, and nimbus are rain-bearing clouds. All these groups are then subdivided with the following prefixes according to the height of their base. Cirro, if the base is high, above 16 to 20,000 feet. Alto, if the cloud base is medium, above 6,500 feet, and no prefix for low-level clouds with bases below 6,500 feet. This means that we can have cirrocumuliform, altostratus, nimbostratus, and altocumulus, and many more. If cumulus clouds are present in the morning, you can expect cumulonimbus later in the day. Radiation fog forms on cloudless nights where the surface loses heat through radiation. The ground will then be cooler than its surrounding air. If this air is relatively moist, the ground will cool the air past its dew point, forming fog. Light winds aid this process. Radiation fog only appears over land. If there is no wind at all, dew forms, or frost if the surface temperature is below zero. Advection fog is similar to radiation fog in that it is formed by warm air being on top of a cooler surface, but advection fog generally refers to air which is pushed into that area. For example, advection fog can form over the sea and be pushed into land where it can persist for days. Frontal fog usually forms in the cold air ahead of an approaching occluded warm front. Virga is the phenomenon in which rain falls from a cloud but evaporates before reaching the ground, in a lower, drier, and warmer air mass. Virga may indicate a temperature inversion and, more importantly, possible wind shear. Cumulonimbus clouds are associated with thunderstorm. For the formation of these clouds, there must be a few factors present. 1. Moist air. 2. A trigger for the air to start lifting, such as convection, turbulence, frontal or orthographic lifting. 3. A diabatic cooling of the rising air. And 4. An environmental lapse rate which is greater than the saturated adiabatic lapse rate. This provides an instability and allows the air to keep rising once it has started to do so. Cumulonimbus clouds have 3 stages: the developing stage where air starts to move up, the mature stage where hardcore convective activity is going on inside the clouds, and updrafts or downdrafts of 3,000 feet per second are simultaneously present. There are potential for microbursts, hail, icing, and severe turbulence. And then there is the decaying stage, which happens after the thunderstorm, where sporadic showers and wind shear may still occur. Cumulonimbus should be avoided by at least 10 nautical miles horizontally, and in severe cases more than 20 nautical miles, due to the various effects which are detrimental to flight safety. Wind direction is given as a magnetic when given by a tower for purposes of pilot alignment with the runway, or when relating to upper winds for alignment with high altitude routes and flight planning. A veering wind is a wind which changes direction clockwise. For example, 160 at 10 knots turning into 190 at 10 knots. A backing wind is a wind that changes direction counterclockwise. Buys-Ballott's law states that in the northern hemisphere, if you stand with your back to the wind, a low-pressure area will be to your left. It is the opposite in the southern hemisphere. In the northern hemisphere, wind traveling from a high pressure to a low pressure area will be deflected to the right by the Coriolis force. This force is stronger the further you go from the equator. Eventually, and usually 2,000 or more feet aloft, the pressure gradient force will balance with the Coriolis force. This creates what is known as a geostrophic wind, which is a wind that moves parallel to the isobars, in which situation we assume that the isobars are straight from east to west. Since isobars are not often completely aligned east to west and are often curved around the centers of high and low pressure, in reality there's a third force involved, the centrifugal force. When accounting for this force, a calculated geostrophic wind becomes what is known as a gradient wind. Please follow this link, which is on the screen right now and also in the PDF, to learn more about these winds. Two columns of air with differing temperature gradients will generate a wind aloft. These upper winds will exist even if there is sea level pressure of both columns is the same, because as temperature decreases at different rates, the pressure at certain altitudes will be different. Upper winds are a vector sum of all these forces and those of gradient winds. The direction of a thermal wind is parallel to the isotherms, lines of equal temperature. These thermal winds are found at greater heights. Closer isotherms create a stronger wind, and with your back to this wind, the low temperature will be on your left in the northern hemisphere. Jet streams are the most common example of a thermal wind and are concentrated upon narrow bands where the isotherms are the closest. It must be greater than a 60-knot wind to classify as a jet stream, and these are typically 1,500 nautical miles long, 200 nautical miles wide, and up to 12,000 feet deep. The polar front jet stream is the most popular. It is found at 60 degrees of latitude, where the polar air meets the subtropical air. It is the strongest jet stream, more so over land in the winter. The intertropical front jet stream is found where the subtropical meets the tropical air, roughly at 30 degrees latitude. The strongest cold air turbulence can be found on the cold side of any jet stream. In the northern hemisphere, winds weaken and back. For example, 180 degrees at 30 knots at 2,000 feet, and 150 degrees at 15 knots at the surface. In the southern hemisphere, it is the opposite. Wind weakens and veers. These veering and backing effects of the surface wind are much stronger during the night. Important note: a huge misconception in most aviation books is that veer and back relates to the relative movement of the wind. This is wrong. A wind cannot back with a decrease in height and simultaneously veer with an increase in height. A backing wind will always be a backing wind, in which it will always shift counterclockwise with a decrease in height. So it is obvious that it will shift clockwise with an increase in height, however it will still be called a backing wind. For clarity, a wind which blows from 230 degrees at flight level 020 and 130 degrees at the surface will always be called a backing wind, regardless of whether you are climbing or descending. End of important note. Trade winds are persistent winds which blow from subtropical high-pressure belts towards the equator, from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. Foehn winds are very interesting. As wind blows up a mountain, it crosses its dew point and cools at its saturated adiabatic lapse rate, as well as losing moisture. On the other side of the mountain, it will descend and warm at its greater dry adiabatic lapse rate. meaning that after the air passes the mountain, it will be warmer and drier on the other side. Low pressure system. A low pressure system will typically have more than one air mass within it, such as a warm air mass incorporated into a cold air mass surrounded by fronts. Surface pressure decreases as you move towards the center of the low pressure system. Airflow converges at the lower layers, rises at the center, and diverges in the upper layers. This convergence and rising is what gives way to cloud formation and cumuliform, as well as the associated precipitation phenomena. Lows have steeper pressure gradients than highs. They move faster and are more short-lived than highs. Tighter isobars also create stronger winds inside low-pressure systems. In the northern hemisphere, wind flows counterclockwise into a low-pressure area. If a plane is flying towards a low, it will experience right drift, compensated with right rudder or a left heading correction. Depressions, or low-pressure systems, can be categorized as frontal, thermal, tropical storm, and orthographic depressions. Vertical motion causes the visibility in these low-pressure areas to be good, as particulates will be carried out of the atmosphere upwards. Frontal weather is to be expected. A trough is a V-shaped protrusion of a low-pressure system. Air flows into a trough and then rises, giving way to cloud formation and possibly thunderstorm activity. When flying from a high to a low, your indicated altitude will be higher than your true altitude. High-pressure systems are categorized by the greater space between isobars. This means weaker or calmer winds. Airflow in high-pressure systems converges in the upper layers, flows downwards, and then diverges in the lower layers. These systems last a bit longer, but they move slower and they are calmer. They will have little to no defined fronts within them. Wind circulates clockwise around a high-pressure system in the northern hemisphere. High-pressure systems are characterized by clear upper skies where any cloud and precipitation is dispersed. Winds are light and visibility may be poor at low levels. A ridge is the opposite of a trough. It is a U-shaped extension of a high-pressure system. Air subsides into it and anticyclonic weather will be found within its vicinity. A front is a boundary between two air masses. They are most often found in low-pressure systems where two or more air masses can be found. Frontal activity describes the interactions which takes place as one air mass replaces another over a particular piece of land. Frontal depressions developed when two air masses meet but do not mix together because one is warmer and therefore less dense than the other, like olive oil in water. These depressions are what drive most of the weather on Earth and can be seen in the diagram. Since warm fronts slope upwards, their forward limits are much further than the line depicted on a weather chart. The cirrus clouds at the tip of the front can be as much as 600 nautical miles ahead of the line on the weather chart. Atmospheric pressure falls as a warm front approaches. Chapter 9. Flight Operations and Technique. NOTAMs can be Class 1, More Urgent, or Class 2, which are published in the NTAP every 28 days. The minimum height rule states that an aircraft should not fly less than 1,000 feet above the highest obstacle within a 5 nautical mile radius, unless it is necessary in order to land, unless the aircraft has been authorized by the competent authority to do so, unless the aircraft is flying below 3,000 above mean sea level and clear of clouds, but ICAO also states that this minimum height must be increased to 2,000 feet above the highest obstacle within 5 nautical miles if you're in a mountainous region. The lowest usable flight level is the minimum altitude on an airway which is at least 1,000 feet above the highest obstacle within 15 nautical miles of the airway centerline. The lowest usable en route flight level must be 500 feet above this altitude. Weather minima for an approach are expressed as a decision height or a minimum descent altitude or as a runway visual range. RVR is measured and reported at the touchdown point, the midpoint, and the endpoint of the runway. A port side wind in the northern hemisphere means that you're flying towards an area of low pressure. A left crosswind can be trickier during a landing in the northern hemisphere because of the typical movement of the wind when decreasing in altitude. For example, when on approach to runway 36, wind from 310 at 1,000 feet may become wind from 270 at 200 feet, increasing the crosswind component. The ICAO aircraft categories are as follows. Heavy aircraft weighing more than 136,000 kilograms and are required to identify as heavy on initial contact. Medium aircraft are from 7,000 to 135,999 kilograms, and light aircraft are those weighing less than 7,000 kilograms. The standard circuit is left turns, and the standard holding pattern is right turns. The following image explains VREF corrections to be applied depending on the wind or gusts present. For example, if your normal approach speed is 120 knots and a headwind component of 20 knots gusting 28 knots, 120 plus 10 plus 8 gives you an 138 knot approach speed. Autothrottle is generally used rather than mental calculations. It is in the control display unit. Ground effect is caused not only by the reduction of downwash, but also because drag-producing vortices are eliminated, so the aircraft slows down at a decreased rate when close to the runway. Light aircraft must be separated by 6 nautical miles or 3 minutes from heavy aircraft, 5 nautical miles or 3 minutes from medium aircraft, and 3 nautical miles from other light aircraft. Here's a refresher for instrument flight rules flight. When the tower says you're cleared for approach, this does not mean that you're cleared to land. It means you've been approved to begin the initial approach point. It is basically a clearance to fly down to the decision point. The standard holding pattern direction is right-hand turned, making non-standard holds left-hand turns. It is important to note that the sector of entry is calculated using aircraft heading, not aircraft track. Holding pattern legs are 1 minute below 14,000 feet and 1.5 minutes above. On an ILS approach, you may descend when you have been cleared for the procedure, as well as when you have the localizer captured within 5 degrees. To calculate distance from threshold at which you would intercept the glide slope in nautical miles, divide the height by the glide slope angle times 100. For example, 3,000 feet divided by 3 degrees times 100 equals 10 nautical miles from threshold. To calculate the intercept height for the glide slope at a particular distance, multiply this nautical mile distance by the glide slope angle times 100. For example, 10 nautical miles times 3 times 100 equals 3,000 feet. Glide slope angle is equals to your percentage gradient times 0.57, and 5 times your ground speed roughly gives you the rate of descent for a 3-degree glide slope. On screen now are the ILS minima for each approach category. The final approach fix should always be crossed at or above the intermediate height before final descent can be initiated. On screen now are the standard 45-degree procedure turn, an 80 to 60-degree procedure turn, as well as the typical angles for the airplane navigation lights. emergency frequencies are 121.5 and 243.0 VHF. Head-on, both aircraft must turn right to avoid a collision. If at a constant bearing, the aircraft which has the other to its right side must turn right to avoid. If overtaking, the aircraft being overtaken has the right of way. The overtaker must do so by the right side. The red anti-collision light should be on whenever an engine is running. The white strobe light should be on whenever an aircraft is airborne. Nav lights should be on at night, but are recommended at all times. To continue a non-precision approach below minimum descent height, one of the following must be identified: the aerodrome lighting system, the threshold, its markings or its lights, the visual glide slope indicator, such as a PAPI, the touchdown zone lights or markings, or the runway edge lights. To continue a precision approach below decision height for Cat 1 approaches, you must see the aerodrome lighting system, the threshold or its markings or its lights, a VGSI such as the PAPI or the VASI lights, touchdown zone lights or markings, runway edge lights. To continue a precision approach below decision height in Cat 2 operations, a visual segment containing at least 3 consecutive bulbs must be seen from the centerline of the aerodrome lighting system, the touchdown zone lights, the runway centerline lights, or the runway edge lights. To continue a precision approach below decision height for Category 3A, a visual segment containing at least 3 consecutive bulbs must be seen from the centerline of the approach lights or the touchdown zone lights or the centerline lights. Holding point markings on an aerodrome. If you approach from the dotted side, you may cross at your discretion, but if you approach from the solid side, you need a clearance, such as a takeoff clearance, in order to cross. This completes Chapter 9 and all of our ACE summaries. If you have any questions, please leave a comment. These summaries obviously don't cover everything you need to know for an interview or even anything in the book. These are just the points that I personally found more interesting and more important to know. Subscribe and like so that we can see more videos and provide you with more information. Thanks for watching.